Hello and welcome to this video tutorial, which is part 2 of the AS Physics Paper 1 of the May-June session 2022. In this part of the tutorial, we will look at question 11 all the way to question 20. Again, I continue to appeal to you to take a second and subscribe to my channel if this is your first time here. This is important as it is one of the ways of getting feedback from my viewers. Another way of showing support for my work is to like the video and share it where possible. And without wasting time, let's go to question 11. In question 11, we are asked, or rather we are told, a horizontal wooden plank is pivoted at one end as shown. So there's a pivot, there's the wooden plank, and other details are given as far as dimensions are concerned. The plank has a mass of 100 kg and a length of 10 meters. The center of gravity of the plank is at the 4 meter from the pivot, at 4 meters from the pivot. What is the question? What is the moment of the weight of the plank about the pivot? Moment of the weight of the plank from the pivot or about the pivot, because we always take moment about a point. So weight of an object usually acts through its center of gravity. Its center of gravity. So this is the center of gravity or the center of mass of this pivot, and this is where the weight of this plank is going to act. And the weight of an object is going to be given by its mass times the value of the gravitational field strength. So we are going to have 1000 newtons acting at this particular point, and its moment about the pivot will be 4 meters times about 1000 newtons, and that will be about 4000 newton meters clockwise. So that answer should be this one, part C. But maybe you may use the value of G as 9.81. It really does not make much difference because the answer is so close to 4000 Newton meters clockwise. And that is how we work out that part of the question. Let's go to question 12. In question 12, we are asked, when must an object be in equilibrium? Here we are talking about the conditions for equilibrium. There are two of them. What are they? Resultant moment is 0 and the resultant force is 0. It's just as simple as that. Or you can say the principle of moment is going to apply. Okay? When no resultant force acts on the object, in other words, the resultant force is 0, this one is just one of the conditions. There are two conditions. When no resultant force and no resultant torque, the other term for moment is torque, act on the object. When no resultant torque acts on the object, it is the second condition for equilibrium. Like I said, here we are looking for the two conditions. When the upward force on the object is equal and opposite to its weight, this is an application of the second condition, where we are talking about the resultant force being equal to 0 means that the sum of forces in one direction, which may be upwards, should be equal to the sum of forces in the opposite direction. So this one is a specific application of this one condition. So the best answer here is B, when no resultant force and no resultant torque act on the object. Question 13. What are we told in question 13? We are told this. A uniform diving board is held by two fixed rods at points P and Q. A person stands at end R of the diving board as shown here. The forces exerted by the rods, on the board. For example, this rod exerts a force upwards on this board. This stop or rod exerts a force downwards on this board. So you must know their directions. The board remains in equilibrium as the person slowly moves towards point Q from end R. So the weight of this person is not changing. So the weight of this person has moment about this point. For example, if we were to take moment about this point, okay, if we take moment about this point, we'll find that the anti-clockwise moment of the board will be the force on the board at R, which acts this way, which will be anti-clockwise, and the clockwise moment will be the weight of this person about this particular point. So as this person walks towards the rod, maybe this person is at a point here, okay, the distance from the point about which we are taking moment to the weight of that person is going to be small, and therefore the clockwise moment will be small, okay, will reduce. That means the anti-clockwise moment, which will be due to this force times this distance, must also reduce, because the principle of moment applies. The sum of the clockwise moment, which will be the weight of this person times this distance, should be equal to the force at point P times this distance. And since the moment due to the weight of this person has reduced or reduces continuously as the person walks towards point Q, and we know why it is reducing, then the moment due to the force at point P must also reduce. So in order for that moment to reduce, it is the force which will reduce, because this distance is not changing. So this force must become smaller and smaller as this person walks towards point Q. What will happen to the force exerted on the board by this rod at point Q, which is vertically upwards? Observe that when I take moment about this point, the moment due to the force on the board at point Q becomes 0, because the distance is 0. That's why the force at point Q does not feature anywhere. But we know that it is there. If we apply the second condition for equilibrium, which said that the resultant force on the system must be 0, we find that this weight of this person plus this weight, which has reduced, should be equal to the force at point Q, which acts vertically upwards. In other words, the sum of the upward forces should be equal to the sum of the downward forces, but the sum of the downward forces is reducing, and since equilibrium must be maintained, then the force acting on the board at point Q is also reducing. So as this person walks towards point Q, the force acting on the board at point P reduces, and that acting on the same board at point Q reduces. Okay, so that is how we would try and answer this question, because we asked which rod describes the changes to the magnitudes of the forces exerted by the rods on the board. Both of them are going to decrease. They are going to decrease. Let's look at question 14. In question 14, this is what we are given. A solid block has sides of length L, 2L, and 4L. The block is submerged in water of uniform density so that the faces with the largest area are horizontal as shown. This is the surface of the water, okay? So 2L, 4L, and L as shown. The upthrust acting on the block is U. The block is now rotated to a new position so that the face with the smallest area are horizontal. The face with the smallest area is this one, L times 2L, okay? Or this one, L times 2L. That is the face which is going to be horizontal. The block remains fully submerged in the water. So nothing happens to the upthrust. The upthrust remains the same, because upthrust is equals to the weight of the fluid which is displaced. So, and since the volume of the fluid displaced does not change, then it means the upthrust remains constant. What is the upthrust acting on the block in this new position? It will simply be U. It will not change. Upthrust is equal to the weight of the fluid displaced, and the weight of the fluid displaced is equal to rho Vg, where rho is the density of the liquid, V is the volume of the liquid displaced. In this case, it will be equal to the volume of the block, which does not change. And of course, G is the gravitational field strength. That is why the upthrust does not change. Let's look at question 15. In a large container in an oil refinery, 3 oils of different densities are mixed. No chemical activities occur. The mixture consists of 1200 kgs of oil of density 1100 kilograms per meters cubed, 1500 kgs of oil of density 800 kilograms per meters cubed, 400 kg of oil of densities 910 kilograms per meters cubed. What is the density of the mixture? In order to get the density of the mixture, we need to divide the total mass of the mixture, which will be 1200 plus 1500 plus 4000, divided by the total volume of the mixture, which will be equal to the volume of this oil of this much density plus the volume of this oil plus the volume of this oil. So we can use mass and density to get the volume of this oil. In all of them, we are supposed to calculate the volume, V1, V2, V3, so that now we add all the 3 volumes, and then we add all these 3 masses, 1200 plus 1500 plus 4000, divided by V1 plus V2 plus V3. And that is how. So if you follow those steps, you will find that the density of that mixture is 927 kilograms per meters cubed. Let's go to question 16. In question 16, we are given that a box slides down a rough ramp. So the mention of the word ramp means there is friction force acting in this direction. The change in the gravitational potential energy of the block is 16 joules. Change in gravitational potential energy. Actually, this will be a loss of 16 joules. So if we were to treat it like a gain in gravitational potential energy, we will say the gain in gravitational potential energy is minus 16 joules. The negative sign will indicate that that potential energy has decreased by that value. So we have been told that the change in gravitational potential energy is 16 joules as it moves between the positions X and Y. The box has 24 joules of kinetic energy at X, so it is already in motion, and 35 joules of kinetic energy at Y. So its speed is obviously increasing. So the gain in gravitational in kinetic energy can be worked out. It will be the final kinetic energy minus the initial kinetic energy, which is 24. So 35 minus 24 will give us the gain in kinetic energy. How much work is done against the friction force? In this question, we can use the concept of the principle of conservation of energy, where we are going to talk about the work done by any external forces on an object is equals to the gain in energy of that system. This is what that principle talks about. That if work is done on a system of forces or on an object, then that object gains energy. The 2 types of external forces which are acting on this object will be the driving force and the frictional force. In this case, we find that there is no driving force because this object does not have any kind of engine, and therefore the only external force acting on that object will be the friction force. So we can talk about the work done by friction force being equal to gain in energy. So this gain in energy, I can reverse this and now say gain in potential energy plus gain in kinetic energy is equals to work done by the driving force plus work done the friction force. This is supposed to be friction force. This is supposed to be F, friction force. So because this one is interpreted to be like a gain in potential energy, that is why there is a minus sign here. After all, if even when we consider a situation like this one, and we can see that it is moving down the slope, we know that there is a decrease in the vertical height. That is why the gain in gravitational potential energy, and notice that I'm using the word gain in gravitational potential energy. The gain in gravitational potential energy must have a negative sign, because obviously it is losing height. However, the gain in kinetic energy is going to be equal to the final kinetic energy at point y minus the kinetic energy at point x, is equals to work done by the driving force is 0, and this is work done by friction force. So once we manipulate this, we are going to find that the work done by friction force is minus 5 joules. The work done by friction force is minus 5 joules. Let's look at the question, what it is asking. How much work is done against, you see this word here? So the moment we replace the work done by friction force with the word against, so that the statement reads work done against friction force, then we simply ignore the negative sign and we find that it is just equal to 5 joules. This is similar to situations whereby you were asked to find the deceleration of an object. When they do that, remember there is no equation which asks you to calculate the deceleration of an object. All questions ask you to calculate or involve the acceleration. So the moment you see that the acceleration has a negative sign and you call that acceleration a deceleration, the negative sign always disappears. So this kind of working may be new to you, but it is one of the simplest ways of working out this kind of question that involves energy. Always remember this: work done by external forces, and I emphasize this word, work done by external forces, and the two external forces are friction force and driving force, is equals to gain in energy. The gain in energy consists of the gain in gravitational potential energy and the gain in kinetic energy. Remember that. And then identify situations whereby there is no driving force. Therefore, the work done by the driving force will be 0. Identify situations whereby if we are told that the ramp is smooth, then it means there is no friction force and the work done against friction will be 0. So try out this when you encounter questions of this nature, and it will not fail you. If, for example, you try a question and find that this is not working, just let me know in the comments below, and I'll show you how it is applied to any question which involves energy. Let's go to question 17. In question 17, we are told that the total energy supplied to an electric motor is E, energy Q is wasted, and the remaining energy does useful work. What is the efficiency of the motor? Let's look at the physical quantities given. Total energy supplied to the electric motor. This is the energy input. Energy input. Energy Q is wasted, so the useful energy will be E minus Q. Useful energy will be E minus Q. How do we calculate efficiency? It is work output over the work input. The work output is E minus Q. Because remember, energy Q is wasted, which means useful work done by this energy is E minus what is wasted. That is useful work done. And then efficiency is the ratio of the useful work done to the energy input, like that. So when we manipulate that, we are going to get this. Efficiency is work output over work input. Work output is input, total energy put into the system minus the energy that is wasted, divide by work input, divide by E. Of course, when we separate these equations so that we can have E over E minus Q over E, then E over E is 1, then we get this, and that is why our answer is C. Let's go to question 18. Objects with different masses are placed on the horizontal surface of a table. The objects are then raised to different heights above the table. The gain in gravitational potential energy of each object is the same. Which graph best shows the variation of the height of the objects above the table with their mass m? Okay, so here I have the situation. What do we have? We've got a mass of 2 kg, for example, and a mass of 4 kg. Objects with different masses, okay, placed on the horizontal surface of a table. The objects are raised to different heights above the table. So this one is raised to 2 meters, and this one could be raised to 4 meters. Find that the gain in energy here will be mgh, here it will also be mgh, gain in gravitational potential energy. The gravitational potential energy of each object is the same. So this one must be raised to half the distance of this one for the gravitational potential energies to be the same. After all, potential energy is mgh. Since g is the same, then 2 times g times 4 should be equal to 4 times 2 times g. So the heavier one must be raised to a lesser height. Which graph best shows the variation of the height h of the object above the table with their masses? So when the mass doubles, the height is halved. When the mass doubles, the height is halved. And that is an inverse kind of relationship, and that is where the answer is A. You can say that when the mass is doubled, the height through which it is raised is halved if the gravitational potential energy is to remain the same. Let's go to question 19. In question 19, we are given that 2 wires, P and Q, are made from the same metal and hung vertically from a steel girder. Wire Q has half the length and twice the diameter of wire P. Identical masses are attached to the bottom of each wire. Both wires obey Hooke's law as they are stretched by the weight of the masses. What is the ratio of the extension of P to the extension of Q? So we are going to calculate the extension of P and then work out the extension of Q and then divide that extension by this extension. Okay, so let me take you through the process of working out this question. I worked it separately at this particular point. I'd like you to bear in mind that we are dealing with this steel cable of length L and diameter D. This is P, while Q has got twice the diameter and half the length. Okay, so the cross-section area is pi r squared, where we've got pi. R is d over 2. I square that, I get pi d squared over 4. The stress will be force over area, which will be equal to F divided by the area, which is pi d squared over 4. And when I rearrange, I got 4F pi d squared. The strain will be given by the extension of P divided by length L. All right. So the Young's modulus of that particular wire will be equal to stress over strain, and I get this expression. When it comes to Q, I'm going to get the radius as 2d over 2, which is d, and therefore the area will be pi d squared. The stress will be F over A, where A is a cross-section area and the area is this much, where I get F over pi d squared. The strain will be the extension of Q divided by L over 2, and I get 2 EQ over L. The 2 just becomes the numerator, and that is where it multiplies the extension of Q. Now, again, the Young's modulus is given by stress over strain, that is for Q, and that is the expression that I get here. Now, since this material is the same, the Young modulus is the same. The Young modulus of wire P is equal to the Young modulus of wire Q. And when you look at this expression, it simplifies to a very simple expression here, where we get 1 over the extension over Q is equal to 8 over the extension of P. It's just a matter of rearranging this equation so that it reads extension of P divided by the extension of Q, which is 8 over 1. And this is what we've been asked to calculate. So question number 8 is one of those questions which is appears to be very long, and sometimes the students get discouraged and they do not know where to start. It is always very easy. You always look at first principles. By first principles, I had to consider, because you might ask me, what made you follow that route? When I look at this question, these are 2 wires made from the same material, the same metal. That means the Young modulus, what is common between them could be their density is the same, the value of the Young modulus is the same. Why am I centering on Young modulus? Is because of the dimensions. The cross-section area is being mentioned, the forces exerted is being mentioned, extension is being mentioned, and that is where I have to think about what is common between them. So you take one metal, you work out the Young modulus, you take the other metal, you work out the Young modulus, and then you know the Young modulus does not change. It is just like resistivity of a metal. If I were to work out the resistivity of this metal P, it should be the same as the resistivity of metal Q, because they are made from the same metal. Another thing which is common between them is the density. The density of P and the density of Q is the same because they are made from the same metal. That's how you would approach questions of this kind. However, go through my working, because in my working I've shown you a lot of things that you can be able to revise. Let's go to question 20. In question 20, this is a question where we've got to make a decision just by looking at the various parts. Which statement about elastic and plastic deformation must be correct? Elastic deformation and plastic deformation are proportional to the applied force. Elastic deformation and plastic deformation are proportional to the applied force. This is not true. This is not true. For plastic deformation, the deformation is not proportional to the applied force. Elastic deformation and plastic deformation causes no change in volume. This is true. Elastic deformation causes heating of the material, but plastic deformation does not. Both of them cause heating of the material. Elastic deformation is reversible, but plastic deformation is not. This is true. D is true, and that is why D is the correct answer. Let's stop at this point. In the next video, I'm going to look at questions 21 to 30.